Hello, good afternoon. Unit 5 Chemical Bonding under BC first year at Tribhuvan University, Institute of Science and Technology, Chemistry, BC first year. First of all, ionic bond or bionic bond by complete transfer of electron between metal and non-metal atom forming cation and anion is called ionic electrovalent bond. For example, sodium 1 electron donates to chlorine for complete octet and also complete the octet of sodium. So such kinds of attraction, electric force of attraction between sodium and chlorine is the ionic bond. Hence, ionic bond is electrostatic force of attraction between cation and anion. Nature of bond: an ion can attract the other ion having the opposite charge from all directions. Therefore, ionic bond is non-directional in nature. Factors affecting formation of ionic bond. Ionization potential of metal atom should be low, that is cation form easily. Electron affinity of non-metal atom should be high, that is higher electron affinity favors easily formation of anion. Lattice energy of ionic compounds should be high. In higher lattice energy, then it will be more stable and its formation will be more favorable. Properties of ionic compounds: physical state. All ionic compounds exist in crystalline solid form. They never exist on liquid or gas under normal conditions due to strong electrostatic force of attraction between cation and anion. Melting and boiling point. Ionic compounds have very high melting and boiling points due to presence of strong electrostatic force of attraction holding the ions. Electrical conductivity. In our solid state, ionic compounds are bad conductor of heat and electricity, but in molten state and solution state, ionic compounds are good conductor of electricity due to presence of free ions in these states. Solubility. Ionic compounds are generally soluble in polar solvents, water and liquid ammonia, due to their dielectric constant value. However, ionic compounds are generally insoluble in non-polar solvents, benzene, ether, due to their low dielectric constant. If the solvation energy of ions is greater than the lattice energy, ionic compounds, then it will be soluble. If the lattice energy is greater than the solvation energy, it will be insoluble in polar solvents. The ions have high ability to undergo solvation. Consequently, high solvation energy is released, which exceeds the lattice energy of ionic compounds, and hence it dissolves in their polar solvents. In the non-polar solvents, the ions have no tendency to undergo solvation due to lack of electrostatic interaction between the ions and non-polar solvent. So, no solvation energy released to break the lattice energy bond. Consequently, it remains insoluble in non-polar solvents. Brittleness. Ionic compounds are highly brittle, that is, break into small pieces by applying external force. Ionic compounds are composed of partial layers of cations and anions when external force is applied on it. One layer of anions slide over another such that ions come in front of each other. Hence, the layer begins to repel each other and the ionic compounds break. Radius ratio rule. The ratio of radius of cation to the anion of the ionic compounds is called its radius ratio. Radius ratio, radius of cation over radius of anion, R plus over R minus. Determination of structure of ionic compounds by using the radius ratio of ions is called radius ratio rule. Let us take an ionic compound M plus and X minus into which coordination by M plus 3 ions in the 3 and surrounded by the 3X minus ions. That is the 3 possible arrangement for coordination number 3 are the given below. From radius ratio, we can predict the coordination number and structure of ionic crystal. Among the crystal, the coordination numbers are 3, 4, 6, and 8 are common. The corresponding limiting radius ratio values for these coordination numbers are given below. Limiting radius ratio 0.155 to 0.225, coordination number 3, say planar, and example boron oxides. Less than 0.155, coordination number 2, 0.225 to 0.414, coordination number 4, 0.414 to 0.72732, coordination number 6 of octahedral, 0.732 to 0.998 body center. The shape of crystal predicted from the ionic radius radii of cation and anion. The radius ratio is rarely 1, and in such case, coordination number is 12. The radius ratio are dictated by two factors. The ions of same charge avoid coming in contact with each other. The ions of the opposite charge try to get as close together as possible so that the attraction of the same charge are minimized. The radius ratio rule is applicable to the coordination numbers of cations, and the idea is to check how many anions can be accommodated around cations, and coordination number of anion not need to be the same. Limitations of radius ratio rule: it is useful only to gauge the coordination number of the cation and not anion. It is only applied for AB type crystal satisfactorily, but not the crystal of A2B or AB2 type. High coordination number like 12 predicted by this rule does not occur in the practice. This rule applicable only to crystals made of ions. That's true only when the ionic radii are known accurately. To understand the ionic crystal structure, it is essential to consider not only immediate environment of one ion, but also the infinite three-dimensional character of the structure, which is ignored by the radius ratio rule. Theoretical calculation of lattice energy: the amount of energy released when 1 mole of the ionic compounds is formed from the cation and anion in gaseous state is called lattice energy. It is also defined as the amount of energy required to break 1 mole of ionic compound into cations and anions in gaseous state. For example, Na plus X minus applied energy, Na plus X minus Bond-Landy equation. The Bond-Landy equation is means the calculating the lattice energy of the crystalline ion theoretically. In this method, the ions are treated with as the point charge. According to Coulomb's law, the force of attraction between the opposite charge ion is given by F equal to Q1 Q2 over R square. Q1 charge on ion, Q2 charge on anion, are distance between cation and anion. Now, if one of the ion is moved under the influence of electrostatic attraction by a distance of dr, the work done in this process is given by work done is V equal to dr, Q1 Q2 over R square dr. Integrating the above expression for infinity from infinity to R, total work done, infinity to R Q1 Q2 R square dr, infinity to R Q1 Q2 R square dr, Q1 Q2 minus 2 plus 1. So total work done equal to minus Q1 Q2 R. Total work done is called electrostatic energy attractive energy, Q1 equal to Z plus E, Q2 Z minus E. So the electrostatic Coulombic energy between the two ions of opposite charges given is E equal to Z minus Z plus Z minus E square over R square, E attractive energy, Z plus Z are the charge on the positive and negative ions respectively, electrostatic charge and are the interionic distance. Total attractive energy depends on the number of ions and the geometry of the ionic compounds. Hence, for 1 mole of ionic compound, the equation first should be multiplied by two constants, one which represents the number of ions in 1 mole of the ionic compound, that is Avogadro's number N naught, and another which represents the geometry of the ionic compound. Now, equation first can be written as so that attractive force A equal to minus N not Az plus Z minus square over R, where n is Avogadro's constant 6.023 10 to the power 23, a metallic constant. Value of A depends on the crystal geometry. The value of metallic constant depends on the geometry of ionic compound. All ionic compounds which belong to a particular crystal structure have a particular A value. The value of A of different crystal structure has been calculated theoretically. When positively charged ions come together to form a crystal lattice, it is not only the attractive force that exists, but there is all repulsive force among them. Such repulsive force arises from inter-electronic and internuclear repulsion of two ions. Such repulsion expected to increase with the decreasing interionic distance r. According to Born-Landy, and the repulsive force is given by ER equal B over Rn, where B is the constant called Born coefficient, which depends on the coordination number, and a constant called Born exponent, typically between 5 and 12, often tends to 9 for alkali and halides. Total energy of the crystal lattice is sum of the repulsive force, E equal to A plus ER. So total energy is called lattice energy that holds ions in crystal, hence lattice energy U, static force plus repulsive force, U equal to minus n naught Az plus Z minus C square over R plus B over Rn, question 3. It is possible to evaluate the coefficient of B at a distance where the attractive and repulsive force of positively charged ions are exactly balanced. This distance is called equilibrium distance R naught. Let the equilibrium distance R equal to R naught. So du over R equal to 0. Now differentiating equation 3 with respect to R naught. So du equal to, and differentiating B equal to substituting the value of B in equation 3. So you will get U equal to minus n naught Az plus Z minus C square 4 pi epsilon R 1 minus 1 over n, equation 5. Consequence of Born-Landy equation, Born-Landy constant, that is energy of the ionic compounds is directly proportional to the value of A. It means that lattice energy increases if the value of A increases. Charge and ion lattice energy of the ionic compounds increases the product of charge of ion. That is, the lattice energy is proportional to Z plus Z minus. Interionic distance R naught, lattice energy of ionic compounds decreases if the size of the ions increases. That is, lattice energy inversely proportional to R1 over Rn. Experimental calculation of lattice energy by Born-Haber cycle. Let us take a formation of 1 mole of M in X to formation of X by different ways. So in Born-Haber cycle, determination of percentage ionic character. Percentage ionic character 16 Xa minus Xb, 3.5 Xa Xb. Henry-Smith equation. Polarization. When ions approach each other closely, the cation attracts the electron cloud of the anion, and simultaneously the nucleus of the anion repels the cation. Polarizivity, it is measure of the how easily an electron cloud is distorted by electric field. Dipole moment, Q into D, distance charge. Fazan's rule. A rule formulated by Fazans in 1923 are used to predict whether a chemical bond will be covalent or ionic and depends on the charge on the cation and relative size of cation in anion. Small cation favors covalency, large anion favors covalency. Large charge upon either cation or anion favors covalency. Cation with non-inert gas structure favors covalency. Application of dipole moment, triatomic molecules, tetraatomic molecules, crystal structure, AX type, cesium chloride. Cesium and chloride ions are 160 picometer and 181 picometer respectively, hence limiting radius ratio R plus R minus 169 picometer over 181 picometer. Sodium chloride structure, coordination number 6. Zinc blend D, coordination number 4. Ionic compounds of calcium chloride, lead is 0.73 or above. Titanium oxide, lattice point. The position of each constituent particle in a three-dimensional structure of crystal is represented by a point which is called lattice point. Crystal defect, ideal crystal. They are those crystal in which all the lattice points are occupied by corresponding ions and the interstitial space are vacant. Ideal crystal exists only at 0 Kelvin temperature. Defective crystal are those crystals in which one or more lattice points are vacant and the interstitial space are occupied by ions. All crystals are defective under normal conditions. Impurity defect. In this type of defect, one or more cations or anions both are missing from the crystal and these positions are occupied by some other kinds of ions. Stoichiometric compounds, the ionic compounds in which the cations and anions are present in the ratio represented by their valency are called stoichiometric compounds. These compounds follow the law of constant composition. Non-stoichiometric compounds, ionic compounds in which cations and anions are not present in the ratio represented by their valency are called non-stoichiometric compounds. These compounds do not follow the law of constant composition compounds. Types of defects, stoichiometric defects, defects in ionic compounds which missing of cations and anions do not the stoichiometric ratio of ionic compounds is called stoichiometric defect. Schottky defects, in these defects, ions are missing both cations and anions from the lattice point in the stoichiometric ratio, or the missing ions occupy the surface of crystal. These defects arise in those ionic compounds having similar size of cations and anions, high coordination number. Frankel defects, in these defects, the ions are missing from the lattice points and occupy the interstitial space. This defect arises in those ionic compounds in which cations are smaller than ions. Low coordination number, silver chloride, zinc sulfide, silver bromide. Stability of ionic compounds decreases due to repulsion between ions. Schottky defects decreases density of ionic compounds. Schottky defects, Frankel defects. Non-stoichiometric defects, defects in the ionic compounds in which missing of cations or anions alter the ratio ions represented by their valency is called non-stoichiometric defects. In these defects, the ions are not present in the ratio represented by their valency. Their defects arise by the following two ways. Metal deficiency defects, that is the non-metal excess defects, ionic compounds in which the number of metal ions are greater than the stoichiometric ratio is called metal deficiency defects. Positive ion absent, this defect is produced when one or more cations are missing from their positions and those cations vacancies are produced in order to maintain charge balance. Once or more nearby the cations acquire extra positive charge and those converted into cations with higher oxidation state, example ferrous oxide, nickel oxide, ferrous sulfide. This type of metal defects cause semiconductor and also called p-type semiconductor. Extra interstitial anions, and extra negative ions is present in an interstitial position and to maintain charge balance. For nearby, nearly cation acquires extra positive charge, however, negative ions are usually large. It would be difficult to fit them into interstitial positions. No any examples of crystal containing such negative interstitial ions are known at present. Metal excess defects, F center negative ions absent, and anion may be missing from its lattice side, having a vacancy which is occupied by an electron from its lattice side, having a vacancy which is occupied by an electron to maintain the electrical balance. This type of defects is formed by crystal which is would be expected to form Schottky defects. Extra interstitial cations and electrons, and extra cation occupies an interstitial position in the lattice end to maintain electrical balance. An electron is also present in the interstitial position. This defect is found in Frankel defects. Okay, it's all about BSc first year, chemical bonding, Unit 5, BSc first year chemistry, under Institute of Science and Technology, Trivandrum University. Thanks for watching, and best of luck for your exam, coming exam. That is now. Bye-bye. See you again.